Hello everyone and welcome to the next episode of GPU programming with TNL. Today we will discuss arrays and memory management. First, I would like to emphasize that I will not explain the specifics of programming in CUDA. Our goal is to bypass these complexities by utilizing higher level data structures and algorithms provided by TNL. Before we dive in, let's talk about the programming background you will need. First, you should be comfortable with programming in C. This means understanding loops, conditional statements, functions, pointers, how memory allocation works, and similar concepts of programming in C. Also, you will need some basic knowledge of C++ programming. It's important to know about objects and inheritance, and it would be great if you have some idea about C++ templates and lambda functions. Before we dive into the real programming, let's take a look into this graphic. Here I will show you how the GPU and the CPU are connected. It's really important to understand this. On the left, we have the CPU. It's connected to what we usually call operational memory, but most people just say RAM. In the world of GPU programming, the CPU and this RAM together are known as the host. And the operational memory can also be called the host memory. Now, on the right side, we have the GPU, and it's linked to its own special memory, the global memory. In GPU programming terms, the GPU and its global memory are called the device. You might have noticed the numbers in the diagram. They say how fast the data is transferred from the source to the target. The fastest connection is between the GPU and its global memory. It can be more than 3.3 terabytes per second for the latest NVIDIA H100. The connection between the CPU and the host memory can be more than 760 gigabytes per second for AMD EPYC Genoa with 96 cores, which is 5 times slower compared to the GPU. And finally, the connection between the host and the device is only 126 gigabytes per second for PCI Express 5. It is 6 times slower compared to the CPU and more than 25 times slower compared to the GPU. What implications does this have for us? First, it's evident that the GPU possesses its own high-speed memory, which is advantageous. However, this also implies that any data needed for computations on the GPU must be first moved from the CPU. Once computations on the GPU are complete, results need to be transferred back to the host. Given the slow data transfer rate between the CPU and the GPU, it's essential to minimize this communication. This suggests that offloading minor tasks from the CPU to the GPU might not be efficient, as the time spent transferring data to the GPU could outweigh the time saved by processing on the GPU itself. In general, GPU programming boils down to two main tasks. First, we deal with memory allocation and transferring data between the CPU and the GPU and vice versa. Second, we focus on crafting functions that will execute in parallel on the GPU. We often refer to these functions as kernels. In TNL, memory management is primarily handled using arrays. The array is a templated class found under the TNL containers namespace. If you are unfamiliar with the idea of template parameters, consider them as settings that the compiler uses to customize features of the objects. It's much like selecting options for a new car you are looking to buy. The first parameter value determines the type of elements in the array, defaulting to double. Next we have device, which indicates where the array will be allocated. By default, it's set to TNL devices host, but you can also set it to TNL devices CUDA if you want the array on the GPU. The third parameter index specifies the type used to index array elements. We also have an allocator parameter, but we will not delve into that right now. Here we've got several examples of how to create an array. The first one is an array of 10 integers allocated on the host. The second is an array of integers allocated on the GPU. Next, we have an array on the GPU initialized using a list from the STL library. We can also initialize an array using a vector from the STL library. Lastly, an array can be also initialized using an initializer list. Let's take a look at our first example code for this episode. You can find it in the file name 01 arrayconstructors.cu. To start, we need to include all essential TNL headers, like TNL containers array, TNL devices host, TNL devices CUDA. Now moving on to our main function. Here we are setting up and displaying a series of arrays. The first array consists of 10 integers stored on the host. By default, the array elements are initialized to zeros. Soon we will see it in the output. The next array is also made of integers, but it's stored on the GPU. However, since we haven't specified the size, this array remains empty. The subsequent arrays are also integer based and stored on the GPU. They are initialized using various containers like STL list, STL vector, and lastly, initializer list. To run our example, you can compile it using TNL CXX. After executing, you should expect to see an output similar to this. Here we see that the first host array is filled with zeros, the first CUDA array is empty, the CUDA array list is initialized by the same value as the STL list from the source code on the line 17, CUDA array vector is initialized by the same value as the STL vector on the line 22, and CUDA array init list is initialized by the same value as initializer list on the line 27 in the example code. Apart from using constructors, you can also configure arrays using the setSize and setValue methods. For instance, we first create an empty CUDA array. Next, we define its size as 10. And lastly, we set each element's value to 1. This is also showcased in the code example 02 arraysetup.cu. Here we have the same code as you could see on the last slide. So when you compile it using TNL CXX again, and then you run it, you could see output like this. The array class offers methods to work with specific elements, namely setElement, getElement, and the indexing operator. Both setElement and getElement can be used with arrays on either the CPU or GPU. For arrays on the CPU, these methods work directly. However, when used on a GPU residing array, reading or writing values means transferring the data from the CPU to the GPU or vice versa, which, as we've discussed before, can be very slow. The indexing operator, in contrast, is more straightforward. It doesn't facilitate data transfer between the CPU and GPU. Thus, while you can use it without issues for arrays on the CPU, attempting to use it for an array on the GPU from CPU code will result in a crash. It's safe to use it only within GPU code, but we will explore more about GPU code in some future episode. Let's take a look at the next example. In this example, we start by creating an array on the host, and it's initially filled with zeros. We then modify the first element to 1 using the setElement method. After that, we loop through each element and display their values using the indexing operator. Next, we create a similar array on the CUDA device, again initialized with zeros. Using the setElement method, we modify the first element and print it out to confirm the change. However, when we attempt to print the first element using the indexing operator, the program encounters a crash. Let's see this in action. I will first compile the program using TNL CXX, and now I can run it. As we can observe, the output displays the host array's values at the start, here. We can also see the first element of the CUDA array being successfully modified. But right after that, the program halts abruptly. When in debug mode, TNL CXX compiles the code in a way that it prints the entire stack trace upon a crash. We can see it here. And this confirms that our program crashed precisely where we tried to use the indexing operator on an array located on the GPU, which is here, line 28. The next example is a benchmark, in fact, in which we aim to contrast the efficiency of the two methods, setting each element of a GPU allocated array using setElement and copying data en masse from an array allocated on the host. The fundamental difference is that the former transfers data element by element, whereas the latter does so in a single larger block, which is a method inherently more efficient. Here is how we proceed. We will test it on arrays having a size 128 elements. We first initialize an array on the host, filling it with ones. We then establish a GPU array of matching size. Now, the entirety of the host array is copied to its GPU counterpart using the setElement method, which is here. To track the time this takes, we employ TNL timer, this one. And for a more accurate measuring, we run this operation 1000 times in this loop, and subsequently we calculate the average time here. And finally, we print the average time to the terminal here. Following this, we modify our approach. The element-wise copy within the loop is replaced with a broader assignment operation, transferring all host data to the GPU array at once as one contiguous block of data. This is done here using the assignment operator. Note that this example should be compiled using TNL CXX with the release parameter to activate compiler optimizations. Now executing the benchmark, the results are stark. SetElement method is over 120 times less efficient. It's thus crucial to refrain from using setElement or getElement for GPU allocated arrays in performance sensitive areas of your code. That said, for debugging, data initialization or post-processing, these methods remain useful tools. Note that in both cases the transfer goes through the slowest connection between the CPU and the GPU, yet copying data element by element can make it even slower. Next, we briefly show how to do I/O with arrays. Using the methods save and load, we can save and load a binary image of the array to or from a file. In the following example, we demonstrate this process. First, we create an array on the GPU filled with ones here, and then we save it to a file named array_data using the save method here. Afterward, we create an empty array on the host here and populate it with data from the file using the load method here. To verify, we print the array contents to the terminal here. Upon compilation and execution of the program, we can observe that the host array is also filled with ones, as we expected. We are already nearing the end, but there are two more topics I would like to cover. First, let's discuss array views. An array view is a data structure that simply wraps around already allocated data, without managing its allocation or deallocation. In most other respects, it behaves just like array. The interface of array view mirrors that of array, but it omits methods that might necessitate data reallocation, such as set size, load, and similar. One of the use cases of array view is to use it to wrap up data already allocated within your project to get easily access to the functionality of TNL. It is showcased in the example 06 arrayview.cu. First, we allocate data on the host using the new operator. Then, we step into a code block delineated by curly brackets. This block determines the lifetime of the array view named view that we instantiated within. This view is initialized using a pointer to data here and its size here. Subsequently, we update all elements to the number 7. Once we exit the block, the array view's lifetime concludes, but there is no associated allocation. This behavior is demonstrated when we print the first element of the array on this line, followed by its manual deallocation using delete on this line. Let's check it by compiling it and executing. We see that it works. The last thing to discuss today is writing of the device-independent code. In TNL, it is the template parameter device which says where the data structures are supposed to be allocated and algorithms executed. Thus, we can easily write a code that could be executed on both the CPU and the GPU. All we need to do is to keep the template parameter device even in our code as demonstrated in the last example. The last example can be found in a file 07deviceindependentcode.cu. Here we first implement a function called deviceIndependentFunction. It is this one. It's a templated function with template parameter device, as we can see here. In this function, we first create an array called array, which we can see here. But now we cannot say where the array is allocated. It depends on the parameter device, which was not specified yet. At this moment, it is just a parameter. Next, we set the size of the array to 10 elements, and we set the value of all elements to 1. Afterward, we print the whole array on the terminal using this line of code. And that's all in this function. Now let's proceed to the main function. When calling the device-independent function, we have to provide the parameter device. If we set this parameter to TNL devices host, which we can see here, the array in the function will be allocated on the CPU. If we set the parameter device to TNL devices CUDA, as we can see here, the array in the function will be allocated on the GPU, and also setting of the value of all elements to 1 will be done on the GPU. However, it does not mean that the whole device-independent function will be evaluated on the GPU. I would also like to touch on the CUDA-CC macro that we can see here. This macro is defined only when compiling using a CUDA supporting compiler such as NVCC. Thus, if the CUDA framework isn't present on your system, these two lines of code will be ignored and the execution of the device-independent function on the GPU will be omitted. So now let's compile and execute this example. We see that it works. And that's all in this episode. I hope you have learned something new. I will be very happy if you try TNL. Give me your feedback in the comments below the video and do not hesitate to ask anything concerning TNL. I hope to see you soon with the next episode, and until then, happy coding!